I will now discuss some applications of integration to probability. And some of these things you can find in section 7.8. So, you know the following definitions already. So, x is a random variable on an interval AB. And then we know what the distribution function is. This is denoted by capital F of x, is the probability that x less or equal to little x. And this is now a distribution function on the interval AB. Now, if f of x is continuous, you know that it is right continuous, but if it is continuous and even differentiable, then we can compute the derivative. And we call it little f, and it has the name of the density, of being the density function. So the density function is the derivative of the distribution function. And we call x to be a continuous random variable if it has a density function that is continuous. And of course, this continuity property only has to hold on the interval AB, where x takes its values. Now, of course, not any function can be a density function. There are some necessary properties of a function to be a density function, namely the following. The first one is that the density has to be always non-negative. And secondly, if you integrate over all possible realizations of the random variable x, which is the interval AB, then this means, in fact, the probability that x is between b and a, well, this probability equals 1. So these properties determine whether a function is a density function or not. Now let me give an example. Suppose that x has density function a constant times the power of e, so c is the constant multiplied by e to the minus 1/2 x squared. You know this function already, and we take it to be a density on the whole space. The question is, what should this constant be? Now what we have to check whether the properties are satisfied. Well, this function is always non-negative, so what we have to check is whether if you integrate over the whole space, whether we get 1. So let us do this integration. This is a very hard integral, so I do not expect you to prove that this is true, but what can be proved is that this integral here equals square root of 2 pi. And so we need that the constant times the square root of 2 pi equals 1, so this constant needs to be 1 over the square root of 2 pi. And we call, in this case, we call x a standard normal random variable. Or x has the standard normal distribution. The mean of x is 0 and the variance is 1. Okay, now what properties do we have for a random variable that has a density function? What we know are the following facts: is that the probability that the random variable x lies between the values x1 and x2 is equal to the integral over the interval x1 to x2 of the density function. So probabilities are integrals, and of course these values have to be between the values where x takes its values. The mean of the random variable is the average value of the random variable, so with a probability proportional to the density at the point x, so the probability that x takes the value x approximately is proportional to fx, and then we have the value x and we have to integrate over all possible values of the random variable, and then we get the mean. The variance is denoted by sigma squared, is the deviation from the mean, is the quadratic deviation from the mean. So we can compute it by subtracting from x its expectation, so let's write mu for it, and squaring it, and integrating with respect to the density, because again with probability proportional to little f of x, the random variable takes the value x approximately, and if it takes the value x, then we have to the quantity of interest is the deviation of between x and the mean squared. We can rewrite it as by deleting brackets, so we get x squared minus 2 mu x plus mu squared, and we can integrate this function with respect to the density, and what we get is then the expected value of x squared. This is this first time. Now if we out-integrate over the second term, we get 2 mu minus 2 mu times the expected value, so minus 2 mu squared, and we have to integrate mu squared times the density, which is just mu squared times the integral of the density over the whole space, which is 1. So we get plus mu squared, so we get in total the expected value of x squared minus mu squared. So there's two interpretations of the standard deviation, the sigma squared. But of course you know all these things already. Now if in general you want to compute the expected value of a function of the random variable, then you just get it by integrating with this function with respect to the density.